Hello again. I don't know if I'm very audible right now. So I hope it is audible. If not, I'll just speak in a higher volume. Just give me a moment. So yeah, as the description says, this is now my second live stream, and it's a continuation of the previous live stream, Logic Gates Intro Part 1. In there, I explained the first four logic gates, but now I will explain the remaining four because there are actually eight logic gates. I will wait for like 5 minutes for letting people join. So yeah, we'll wait 5 minutes and then I'll start. I'll just get some other things ready. Also, right now there's a heat wave in India, so uh, have some water nearby because Indian summers are no joke. Just give me a second. Yeah, so even though not many people joined currently, uh, I'll still start explaining. Okay. So first off, let's just revise what we did in the previous part. So well, I discussed what this logic gates are. They're quite literally gates of logic. They specifically are gates that have some uh, rules or logic, you can say, that take in two signals or even more signals, and then they give out some signal. So they allow what can pass or what cannot pass. Now, these are similar to functions in maths, which take into or more inputs. They can also take one input and they give out some output. So the first gate we have is AND. Okay, so I'm gonna just write that down quickly. We also discussed what the truth table is. It's basically a table of all the possibilities and their results when you input something into the uh, gate or function. Okay, so if I have A and B, the truth table for AND will be something like this. Now, AND simply checks if both are 1 or both are true. So, as I posted in the correction video, it's like checking if both have been done. Okay, so an example would be go do the dishes and clean your room. If you have neither cleaned your room nor done the dishes, that is 0 0, then the output is 0. You have not done any of these things, or you have not done things. If you do only one of those, let's say cleaning the room or doing the dishes, that is, then the other one is not done, so you have not done all the things I've asked. But if you clean your room and do the dishes, then you have one. This is similar to multiplication. So in Boolean algebra, A times B is the representation for AND. Okay, AND can also be represented in symbol form like this. So this is A, this is B, and this is C. Remember, these are just signals. Okay, so in actual computer science, these would not be numbers; they would be voltages. So these would be low, 0, and 1, high. Okay, low and high. That's how a computer works. Now, there's also circuit diagram explanation for this, where if you have a battery and then you have a circuit, this bulb is your output, then the switches will be arranged like this to form an AND gate. Okay, so this causes an incomplete circuit or an open circuit. This is new. uh, when both of the switches are open. If only one of them is closed, then still the circuit is open. But if both are closed, then current will have a proper way to pass through, right? Now, I overlooked one small fact, and that is the thing that I've not explained Boolean algebra or have not revised it. So, Boolean algebra is basically comprised of two parts. 1 minute. Boolean alg. I'm just writing alg. Also, I'm still using mouse. I've not gotten a pad or a touchpad for writing, so it's gonna take some time for me. Boolean simply means 0 or 1. This is binary, okay? And algebra is basically how you manipulate these and how they interact. So manipulation and interaction. So Boolean algebra is basically the mathematics of binary and how they interact with each other. So in Boolean algebra, and is a b, just multiplication. This is because 0 times anything is 0. It works pretty well. Now the next gate, this is the first gate. This is the first gate we did. The second gate is OR gate. Okay. Now similar to how English says, the OR gate just checks if at least one of them is done, or at least if one of them is true. So, for example, would you like tea or would you like coffee? Or even better, have you drunk tea or have you drunk coffee? If I have drunk neither, then the answer is no, right? So, false. If I've drunk either tea or if I've drunk coffee, then the answer is one. Yes, I have drunk something. If I've drunk both of them, then still I've drunk at least one of them. So the answer is still 1. This can be considered like addition in Boolean algebra. Only difference is that here 1 plus 1 is actually equal to 1. One of the many topics in computer science which are clowned upon. But yeah, as I said, these are not ones and zeros as numbers. These are ones and zeros as information, as truths, or as voltages. So if you have two high voltages, those two add up to simply a high voltage, right? Yes, it is higher, but it's still a high voltage. So you can think of it like that, or you can just check. for the statement is at least one of them true. One represents true, zero represents false. So one of them is true. Yes, this is true, and that is also true. So the output is also true. That is why one plus one is equal to true. One plus one is equal to one. Almost slipped up into two there. But anyway, uh, as I said before, there's also this symbol for OR gate. So A here and B here. See here, and then the circuit diagram. I need to check from time to time if people are there so that I can just check for viewers. So yeah, we have a slight parallel circuit here. Now here, the electricity has a circuit to pass through, even if only one of the switches is closed. So if this switch is closed, it will pass through here. I don't have to draw the full thing. And if this switch is closed instead, then it will pass through here. So if both switches are closed, it can just take either one of the paths or actually both of the paths. That's what happens in real life. So when both of the switches are closed or any one, then the light bulb turns on. So the circuit is like, okay, is at least one of them closed? Because if at least one of them is closed, only then can the whole thing be done. Next, we have the I found out unary gates. So the third one is called a NOT gate. Now this is similar to what's this? Actual NOT in English. Now here there is, it's like English only. Do not do this, or do not do what I'm doing. So here I have A and here I have C. So if I'm not doing something, then you must do something, right? You're trying to not do what I do. So it's like the inverse or complement in a set. Okay, and if I'm doing something, again, you should not do what I'm doing. So you have to do nothing. Now, for this, you can actually ask it in a question form. Is the answer is the previous question zero, or as I sorry, is the input zero? Now for here it's zero, so yes, but here it's not zero, so no. This zero means true, and zero means false, and one means true. So basically invert. We also call this a negator. Okay. Now the symbol form for this is very simply a bar, or it can also be written as a what's this, dash, or a apostrophe. I'll call this dash or prime because maths. Anyway, the symbol form for this is quite simply a triangle with a circle on the end. Okay, so that's what. And the circuit form is basically a short circuit because we want no current to go when the switch is closed, and we want current to go when the switch is open, right? So now, if I have a switch here, then if the switch is open, then the current will simply pass through here, right? But if the current is closed, because if the switch is closed, then because of the low resistance here, the current will go like this and not pass through here. However, if you actually try this at home, and I don't suggest you try this at home, but if you do, you'll find out that the bulb does not go fully low, fully off, but actually remains slightly dimly lit. This is because of physics, which I will explain later. But basically, it's not that electricity always chooses the path of least resistance. It prefers the path, okay? It basically mostly takes that path. Some of them just take the other path. Now, the fourth gate is the buffer, okay? This is kind of useless, but it just repeats the information like uh, a redstone repeater, as you know in Minecraft. So there, if you have A and C, it just repeats what you say. Zero remains zero and one remains one. This could be used to boost the signal, like previous what is this, transistors, or they were called vacuum tube. I believe they were called triodes. You can search it up if you like. Correct me if I'm wrong. But a small signal there would amplify into a much larger signal. This was because over long ranges, electricity used to, or amperage used to go down. And this was mostly important for uh, morse code uh, Morse code telegraphs, because if you have a low voltage or low amperage, then you cannot exactly distinguish between a dot and a dash. Now the symbol for this is just the input, nothing really changing, and its symbol is like this. Okay, this for Boolean logic, this one, and wait, this one is for Boolean logic, and this one is for what is this? Simple logic circuits. Now for circuit diagram, it's the it's a very simple what is this, homemade circuit. Okay, you just have a switch here and you have the bulb here. So if the switch is off, then no current passes through, so the bulb is off. If the switch is on, current passes through, bulb is on. Very simple. Now, now that we have that out of the way, I have just realized I have run out of this space. So I will be I actually just made this mistake. 1 minute. Uh, Give me a second. Ignore that. Yeah, so this will be part 2, part 1. Slightly weird, but anyway, I've run out of space, so it's allowed. Anyway, where was I? Ah, yes. Those are the first main gates out of the way. Okay. So now I'll have to explain the remaining four. Okay. Now, if you know what those are, you can type in the comments. Although there's not many here, so I'll have to wait. Anyway, now that I've rested enough, time to explain what the other five are. Now, let's look at the fifth one. Now, this is very similar to the AND gate, so I'm going to go from that order, but it's a mixture of NAND gate, AND gate, and or NOT gate. Sorry, I keep messing up. But anyway, it is called the NAND gate. Now, this word is not in English, but it simply means not and. Okay, okay, that's what it very simply means. Now, this truth table for this is actually very similar to and. Okay, so what I'm going to do is I'm going to draw the and not table, so here, and then beside that the NAND not table. Okay, so here I'll have D, which will be the output for NAND. Okay, so C is and this is NAND. Now let's go. 0 0, 0 1, 1 0, and 1 1. Try this out for yourself, and uh, I'll give you the answer in a minute. Anyway, now for 0 0, and will of course be 0, but then remember, NAND gate is just a NOT gate in front of an AND gate. I'll show the diagram later on. Now here, the NOT gate will be applied onto 0. So what that means is the 0 will be inverted, which makes it 1. Now 0 1 is of course 0, so it's again 1. 1 0 becomes 0, which is inverted in 1. But now 1 1 gives 1, which inverted makes 0. So did this is the truth table for NAND gate. Okay, 1 1 1 0. So it just flips the script of AND gate very simply. Now, in practice, you can make an NAND gate like this. So you have an AND gate, and then you have a NOT gate in front of that. So that gives you D. Okay. Because all of these are variants of other gates, I'm going to use A, B, and D, while C is the answer of the previous gate or gates. You will see why I said gates later. But now, the symbol for this is actually pretty simple. It's like this. They're a bit far apart, so it goes like this. It's an AND gate with a circle in front, very similar to the NOT gate. I'm gonna show here. Yeah, so the NOT gate had a circle in front. So the NAND gate also has a circle in front, but its main body is the of the AND gate. Okay. Now that gives you NAND. Now, as for circuital representation, I will come back to that later. I feel like it's more important to say what the gates are, how they function, and then go on to physical practice of how they can function in real life. Now, NAND gate can be represented in Boolean logic as simply sorry, and which has been inverted. Okay, so as you know, AB is AND gate, as I'm showing here. So if you invert it as given here by NOT, you get NAND. Okay. So now the sixth one is similar to NAND, or I hope you can guess it already. It's the NOR gate. Now this is similar to in English, but I'll not really focus on that now. I'll really focus on what it's trying to say. So the NAND gate is asking, is one of them 0? Okay. If you may have noticed, it's also similar to OR gate. So it's asking, is any one of them 0? And I'll get to that point later, how it's similar to OR gate. But NOR gate is, as you know, not OR. I think you've gotten the gist by now. So now here we have D, here we have C. C is the OR gate and D is the NOR gate. To chemistry students, no, this is not Avogadro's number. Anyway, so if I have 0 0, I just set up all the true possibilities first. If I have 0 0, OR will give you 0, right? But then NOR will invert that, so it gets 1. 0 1 gives you 1, which is 0, and the rest of them are also 0 because the rest of them are 1. So because the OR gate gives 1 for everything which has a 1, NOR gate will give a 0 for everything that has a 1. So it's asking, are both 0? And that's similar to AND gate. Now I will get to that again very shortly. So a NOR gate, as you know, it's made up of an OR gate, and then in front of that is a NOT gate. Okay, that's how you get a NOR gate. And the logical symbol for this would be, of course, an OR gate, which has a circle on the tip. Okay, so that's how you make an NOR gate in logic simulators. If you see different types of logic simulators, they will mostly have these chips with OR gate symbol, but with a circle on top. That would be a NOR gate. Now, in practice, like Boolean algebra, of course, you know OR is A plus B, but then if you invert it, you will get NOR gate. Now, I'm going to teach you something which is very fascinating about these two. They are actually very similar to uh, and or an and, not in the fact that they look similar, but they can be expressed in terms of those. Let me explain what I mean. Now, I don't know how many of you know set theory, but there's something called De Morgan's law. Okay, now very simply, De Morgan's laws, they help in explaining one thing of negation in terms of another thing. Here, you, as you know in set theory, it's showing the what's this complement of a union as the what is this, intersection of complements, whereas the complement of an intersection is the union of complements. Now, I'm not going to explain set theory here. I'll explain it in a different video. That is, if you ask for it. But for De Morgan's laws in logic gates, it goes like this: the inverse of A and B, or not A and B, can be expressed as not A or not B. Or actually, I'll just write in Boolean algebra: A or not B. We'll see this in a minute. And A plus B, or nor A and B, or A nor B, that can be expressed as, you guessed it, A naught times B naught. Now notice thing here, notice something here. These two are separate, okay? We're taking A naught separately and B naught separately. Here we're taking A naught separately and B naught separately. They are not to be interconfused. This is not equal to this. Uh, not A and B is not the same as not A or B. Now I'll show what I mean by this. So if we have A and B, if we have not A plus not B, and we have not A and B, then we'll see how they match up. So we have 0, 0, 0, 1, 1, 0, and 1, 1. Now not A would be 1, not B would also be 1. So you get 1. Now here one of them is 0, and or just really cares for one of them. So we get 1 here again. We'll just simplifying things here. So we have another 0. So that becomes 1, and we get 1. But here we have two ones, which becomes 0 and 0 because of the not. So we get 0. Now let's look at the inverse of and. We have 0, 0, that becomes 1. 0, 1, which is 0, so it becomes 1. We have 1, 0, which becomes 0, so again 1. And finally, we have 1, 1, which remains 1, so we get 0. Now, here's the thing: if two truth tables match, then the functions must also match. Okay? It's similar to in maths. If the domain and range of functions match, then the two functions must be the same. Well, not exactly, but you get the idea. If the outputs, if the same inputs give the same outputs, then the logic gates must be the same. Apologies for that function example. That's pretty not a pretty good example. I have to get used to speaking very loudly because my throat is itching a bit. But anyway, I'm doing it for education. It's worth it. Anyway, let's do De Morgan's law on here, or at least verify it. Let's take A naught and B naught. Just excuse me. And let's take not A plus B. Okay. So now think it over a while. As I know, I've already taught you or, I've taught you not, and I've taught you and. So think about what this would be, and I'll just be back in a minute. Anyway, now I'm back. So here, if you have done it already or not, it doesn't matter. But still, it would be better if you have done it. Now here, a naught would be 1 and b naught would also be 1. So if you multiply those together, you get 1. Here you have 1 and then 0. If you multiply those together, you get 0. 1, 1 0 becomes 0, and 1 1 becomes 0 0, which becomes 0. Now let's go to NOR. Okay, this becomes 0, but it's inverted 1. 1 so 0, 1 so 0, and then again 1 so 0. So you can see both of them match exactly. Okay, so that means both of these are same, which just shows De Morgan's law. Not and is the same as not A or not B. Not A or B is the same as not A times not B. That's De Morgan's law for you. If you're in school, they might ask you in CS to prove this De Morgan's law. This is how you do it. You draw the truth table for both and say that because both have the same truth table for the same possibilities, both are the same. Now we're getting a bit sidetracked because we're only on our sixth, and I promised four total. So let's do number 7. Now here's the thing. After this, it goes back to OR again. And this will be exclusive or XOR. Now this is slightly strange, but remember, it's all logic gates at the end of the day. XOR is a pretty useful logic gate which is used in many places. So I'm going to be showing now what the truth table for XOR is. See in the meantime if you can figure out what truth, not truth tables, logic gates have to be added onto each other to replicate an XOR. I'll give you a hint. There are two answers. One is symmetric and one isn't. Now, in the meantime, I'm just going to be drawing the truth tables. Now, A here and B here. Well, we have also D. Now, XOR, as the name implies, should be similar to OR, but it should exclude something. What is that something we're excluding? We'll see. Now, 0 0, 0 1, 1 0, and 1 1. Now, 0 0, as you know, OR is still 0. 0 1 will be 1, 1 0 will be 1. But now here the exclusiveness comes into play. If both are 1, then the output for XOR will actually be 0. It excludes the 1 from the OR list. Okay, if I pull up the OR list, it will be something like this. So you see how this part has been excluded, right? This one has been excluded and become a 0. So now there are two solutions, as I said. One of them is like this. It's a bit complicated, but I'll explain still. You have a NOT gate. You have a NOT gate connected to AND gates. Well, of course, it'll be like this in it. And then both of them are combined into an OR. Okay. So now how does this work? Let's see. If A is 0, if B is 0, it'll be 1 0. So that's of course 0. Same here 0 because it's symmetric. Okay. I can have a line cutting through here and it will be symmetric. So this is also 0. If it's 1 here, then this will be 0, but this will actually be 1. See, the NOT gate here reverses the 0, it gets 1, and the A here remains the same, so it becomes 1. Here we have 1, so the output is 1. If we reverse it the same, but if both are 1, then this will be turned into 0, this will be 1. Same here, this will be 1, but this will be turned to 0. Because AND gates look for both ones, they will consider this as 0, and the OR gate will again give 0. So I'll just draw the diagram in larger size here, because this is a pretty cool what is this logic gate. It's one of the more complex logic gates we have seen until now. Now, of course, the other connection comes from A before it's knotted. And also you can consider these as wires simply. You can make these at home also with transistors, but for now it's better to just trust me. One second. Okay, so this is an XOR gate. Okay, exclusive OR gate. I'll repeat that again. Now this is a bit of a mindful to memorize. So what you can do instead is you can compress it into a logical chip. Okay, even this was what's this doubtful for me. I was doubting if this was the correct one. So this is similar to an OR gate, but instead it's slightly detached. Okay, you can think of the detachment as a symbol for exclusivity. Okay, only some things can pass this gap. And its symbol, now we get a new symbol. Okay, we can expand our knowledge of Boolean algebra and get a new symbol. It's A, and this thing D, B. Okay, so now this is slightly different. Okay, 1 minute. Yeah, there's also another way to show this. It's called the caret symbol. Both are called the caret symbol as far as I'm aware. So both of these are the caret symbol. Now, as you may already know, seeing the XOR gate, this caret symbol checks if both are different. Okay, I might do a what's this overlap video where I explain logic gates with set theory as well, but that'll come later because both are similar. Anyways, the caret symbol checks if A is different from B. Okay, if you pull up our table, A is not different from B, so that gives it false. A is different from B, true. A is supposed to be 1 and 0, sorry. A is different from B, true. But A is not different from B, so again false. And now you may already be wondering about the next one. It's similar to the XOR, and this gate to XOR is similar to NOR to OR. I'm of course talking about XNOR, as you know, exclusive NOR gate. Now let's think about how we can do this. This was the truth table for XOR, right? So I'm gonna use D here. C here, sorry. Something's up with my throat. I don't know what. See here all the possibilities. XOR, as you know, it's exclusive, so 0 1 1 0. XNOR will of course reverse everything that this has done, and so make all his hard work in vain. So it's 1 0 0, but then 1. Now, do you notice how this is very similar to AND, right? So I'll get to that in a bit. It is similar to AND, but it's also similar to NOR, right? Let me just pull up. NOR. It's actually more similar to NOR. Uh, it's also similar to AND in some ways, but no need for that. Now, uh, let's talk about how we can represent this. Now, very easy way is to take this whole chunk and just put a not gate in front of it, right? But I have an idea. How about let's do some Boolean algebra and figure out what we should do. Okay? How do we represent XOR first? So first XNOR will be not, so everything will have a not above it. So then we will have uh, A not times B, as we see here, or because of the or here, B A B not. Okay, some people in calculus may find this similar, but trust me, it isn't. It's very different from this. Now let's expand this a bit. Okay, so as we know from De Morgan's law, this can be expanded into this, right? So now this is our first application of Boolean logic. We can actually figure out how to make stuff. Okay, instead of being stuck in the caveman era, not knowing how to make XNOR. Okay, now again, let's exploit, I mean, use De Morgan's law again to figure it out. So we have A not not plus B not, of course, times A not plus B not not. Now here's the thing. As you know, inverting a number, I'm not going on the wrong place. Inverting a number will give you the opposite number, right? As NOR gate shows here. So inverting that number again would give you the previous number. So that's like two negatives canceling out to make a positive, right? This is A plus B naught times or and A naught plus B. Okay. Now we can draw this in what's this circuital or logic gate way. So if we have A, B, we can simply take this. We'll also have to knot it for later. So we have here. Now we must OR these two together, right? Now we have that. And then we have this, right? So we must, we already did this actually. Or actually, my bad. Sorry, mistakes happen, guys. We can take this and OR it. So that's this part done. And then we can take the other half and then OR that as well. So then this part is done. And then of course we must AND it, right? Because we are multiplying the two together. And there you go. You get the XNOR gate. Let me write that larger for you. Now, this is the reason why Boolean logic is very nice. You don't have to play around with actual circuits or logic gates to try and figure out how these would work. Okay, you just need some thinking time and maybe a cup of water or coffee, whatever you prefer, and just figure it out on your own. Right? That's the beauty of mathematics, or right now the beauty of computer science. You can figure stuff out. Now that's the XNOR gate. Now, of course, we need a shorter form, right? So XNOR is also represented as, you guessed it, an XOR gate with a circle on the top. Okay, not the cherry on the top, the circle on the top. So now this is an XNOR gate. As you know, the Boolean logic symbol for this would be A caret B not. Okay, because we're searching if the two numbers are the same. Okay, here the two numbers are the same, so we get 1. Not the same, 0. Not the same, 0. It's the same, 1. Now you might be asking, but Soham, we have exclusive OR. and exclusive NOR? Why not exclusive and exclusive NAND? Well, let's think about it. What does exclusive and mean? Well, obviously, we have to exclude the bottom one, right? Exclusive means something related to caret, right? What is that? Something related to caret. So let's actually check what X and looks like, shall we? Now, okay, let's just look at this. You'll see why I'm doing this later on, okay? Now we have A, we have B. So we have 0, 0. As per AND rules, that's 0. 0, 1, which is 0. 1, 0, which is 0. And 1, 1, which is again 1. However, for the X and, however, as we know, we should exclude something, right? So we can exclude this 0 because we cannot exclude this 1, right? Because then it'll be off circuit all the time. And who wants a perpetually off light? I mean, if I just turn off this light, if I cannot turn it back on anytime I do, like with this, nothing I do is turning this on, then what's the use of that? So instead of excluding the 1, we can exclude the 0 and put a 1 here. That's X and. Wait a minute, this feels familiar. Oh my god, it's the XNOR. That is right. If you check XNOR gate, it's the same thing. 1001. As I said, if the truth tables are the same, then the functions are also the same. Which is why I made the comment that XNOR is similar to AND. Okay? Same thing goes for XNAND as you're guessing. Okay? If you're checking for this, it will simply be 0110. Okay? So if I do like this, then you can just replace this with XOR 0110, right? You can figure it out on your own. All if you're smart enough. You're watching this, you're probably pretty smart, right? Now that shows why we don't have X and or X no X NAND. Those are just X NOR and XOR. Okay. Now 1 minute. Sorry. Those are just X NOR and XOR. Okay. It's like AI. They already took their jobs. But yeah, that is why we have only 8 and not 10. The other two are redundant. Okay. Now, yes, you can take X and an X NAND as their own gates, but come on, 5 letter short form versus 4 letter short form. What would you prefer? Actually, 3 letter short form, which is even better. So yeah, many people mostly don't take X and X NAND. They mostly take X NOR and XOR. You can be one of the outliers which takes the other ones, but maybe don't. Just a suggestion. But anyway, as I was saying, you can also show XOR as a different way. As I said, asymmetrical, right? That is because I'll get my notes. No, that's not the reason, but I'll get my notes for the actual reason. Yeah, I'm back. This is a separate notebook I keep for my own CS uh, stuff, curiosities, and so on. So now there it says that XOR can be defined as, wait for it, A or B and bad bracket and not A and B. Okay, this is pretty interesting. You see, because we are taking A or B, the normal OR gate, but multiplying with NAND, right? So this is pretty interesting. How about we apply some Boolean logic on it? So that's A plus B times. Well, how about we don't do that first? Okay, because here's the thing: in algebra, as you know, you have the commutative property, not commutative but associative. I'm forgetting stuff. Commutative property, as I said first, where if you have A plus B times C, then you have AC plus BC, right? I hope you remember that at least. Well, same thing we can do here. A times A naught times B plus, well, actually, the whole thing, A times A naught, A B naught times or plus B times A B naught. We're just playing around right now. Now we can use De Morgan's laws and expand this. We have A times A naught, remember, plus A times B naught. Now we have A B times A naught plus B times B naught. Now I want to bring your attention to something here because these are some more new words which I've actually learned in school. I did not know this before. But let's take A and A naught. What does oh my god, what does A naught do? It reverses it, right? So we have different bits. And for AND, we want to check if the bits are the same and 1. But wait, for these two things, this is OR, sorry. For these two things, the result will always be 0, right? So that means for A times A naught, this will always be 0. Same for B times B naught. This is something called a fallacy, okay? So it's a situation where in logic, the answer is always 0, okay? There's nothing you can do it to make it 1. It's like that other word X and, as I showed before, it's like a light that can never be turned on. That's a fallacy. Now, let's take something different. It's not here, but it's still similar. Remember that OR gate? Well, what if we take A and A naught? Well, remember, they're different bits. So if one is 1, then another is 0, and vice versa. So if we have OR, we're just checking if one of them is 1. And of course, one of them will be 1. This is getting a bit confusing. Anyway, if one of them is 0, the other one is 1. If one of them is 1, the other will be 0. And we just need at least 1, right? So this will always be 1. This is called a tautology. Okay, sounds interesting, but it's called a tautology. It's a situation in logic where the answer will always be 1 no matter what you do. It's like a light which can never be switched off. Okay, I can try whatever I want, this light cannot switch off. Of course, I'm pressing other switches, but it's similar. Okay, by pressing some switches or by changing the things, you cannot change the outcome. It's fixed like that. Now, these other ones, they are very similar. So these actually comprise of the XOR gate. How? Well, remember, we're checking if both of them are different. Now, what does this give us? A and not B, and B and not A, right? So that is the definition of XOR. But let's actually think about it, okay? We want to make sure that A not equal to B, okay? So if A is equal to B, then that means A will not equal to B naught, right? In fact, it will be the opposite of B naught. So that means A times B naught will always be 0. Same thing here. A times A naught times B will always be 0 if A is equal to B. However, if A is not equal to B, then one of these will be 1, right? So that means because of tautology, X plus Y will actually be 1. Okay. It's basically this case here, x time plus x naught. This is opposite of this. Okay. Now this is not exact, but you get the idea. You can have a feel for how an XOR can be represented like this. Okay. In fact, if I switch to Google, in fact, I'll try. So, ah, I got it. I have to stop sharing and then share. Now, if I share here, you can see here it's A and not B, or not A and B, or it can be expressed as this, right? Why can't I select anymore? It can be expressed as A plus B times A naught plus B naught, or A plus B times, as De Morgan said, A and B naught. Okay. And if I, no, wait, let me make my life easier. Entire screen, yeah. Here, as we see, A plus A plus B times A and B naught. If we check here, XOR, here we have the same thing. Well, not the same thing, but we have A and not A naught and B here, plus A times B naught, right? This can be, well, not this one, but this can be simple also expanded into this, right? Because here we have it, same thing. So I'll just actually write this down. So yeah, that's it. And for the not gate, it'll actually be the reverse. Not gate, but X naught. So just excuse my voice, but we can take the whole thing. Let me just write it down and then just not it. De Morgan says this. Well, wait. Let me just write what De Morgan says properly. So this times this one. Then De Morgan again said this: A naught plus B times A plus B naught. And notice, this is the exact opposite of this. We have just swapped all the and or. So and or are pretty related, okay? They're like sine and cosine of logic. They're like co-functions. So here we have x nor, and here we have XOR. So now from that, I hope you learned how Boolean algebra works and some of the niche things of Boolean algebra. Not only what's this? 1 plus 1 is now 1. I hope that's not all what you learned. As for, oh my god. As for the circuital diagrams, well, that will be a bit complicated, but I may cover that in a later video, which I might post today. I have to see. However, let's recap what we learned, shall we? We learned what is a what is this, NAND gate. It's the opposite of an AND gate. Okay, it's in the name, EA Sports Part 2. Its symbol is like this, AND gate with a circle on top, and the Boolean algebra representation is A B naught. Next, we learned about NOR, which is used, well, not is used, but its symbol is like this, an OR gate with a circle on top. This circle represents NOT, of course. Its Boolean algebra representation is A plus B naught. Then we took a quick side note onto De Morgan's law. My God, De Morgan's laws, DML, okay, which shows the similarity between and, or, and not. Okay, so it states that not A and B is the same as not A or not B, while A or B or not A or B is the same as not A and not B. Now that's the De Morgan's law out of the way. We move on to the seventh one, which is XNOR. This is a special type of XOR gate which simply excludes the one plus one thing. So now, give me a second. My throat is acting up very badly. I know the stream is going above 1 hour, but I'll finish it fast. It states that uh, one, just not that. It says that uh, is the two numbers equal or not equal. So it checks that if A is not equal to B, right? So that's what it does. Its representation is a disjointed or uh, just separated OR gate, not the circle, of course. Uh, yeah, it does one one as zero. It just checks, okay, and its representation is, of course, as I said, caret. Or as another way, it's like this. And then we have the XNOR, right? XNOR. That simply checks if A is equal to B. Okay. Its representation is a disjoint or just normal XOR with a circle on top, of course. And this is represented as A caret B. I have to really stop writing theta instead of caret. Or, of course, the other kind of caret, not the gold or uh, vegetable carrot, but this other symbol carrot. Now, I also explained how to do some Boolean logic. Pretty nice stuff. We went with the associative law and the commutative law. Commutative law. No, this is not American Sign Language. Sorry. But that's mostly what we did. We also did two more. I'm going to spell them out. To, to, my God. Give me a second. I'm unsure of the exact spelling. I spelled it on the first try correct. Tautology. It is a event in logic that makes something always true. Okay, so result is always true. Example would be A or not A. Okay, that's always true. Then we also learned a fallacy. Okay, what is up with my handwriting with mouse today? This states that it's just a statement that always leads to zero or it's always false, no matter what you do. So an example would be A times A naught, which is equal to 1. Okay. Another example would be, as you may have figured it out, B plus 1. This is always just 1. And another one, B times 0. That actually looks like OB, but 0 times B, that's always 0. That's another example of a fallacy. Okay, so now you know more than what you did before. That rhymes. Good lord. Anyway, I hope you learned something more useful today. Now that's the four things finished, as well as throwing in some more things like a tautology, fallacy, as well as some De Morgan's law, as and also some basic understanding of more Boolean logic and how to use it. Instead of drawing circuits and figuring out what on earth this is happening, you can just start doing maths, and that's the power of maths. You can do nearly anything with it. Okay, maths can predict computers. Hell, maths is even a Turing complete language, but I'm getting ahead of myself. I'll have to explain all of these later. But yeah, later I will explain the uses of these, finally practical applications, and in a short while I will be what's this posting a video related to this about the electrical what's this symbolism for all of these. Okay, like how can I show this in symbolism form? Okay, I'm just showing you again because there is no viewers right now. It's pretty dry desert today. I am just gonna let this load later, and yeah, I'll see you later. However, there's an announcement. Tomorrow, I will be live streaming again, and there, I will not explain the uses. No, I will be making a PPT. I'm just kidding. I am actually going to be explaining the uses for these while also. Oh, wait, that's later. Sorry, I am going to be making a PPT for this, or either Microsoft PPT, or that is going to be for another video, not live stream, but it'll be uploaded video. It's going to be much shorter than 2 hours, because I'm pretty sure nobody's going to watch 2 hours of me rambling on about logic gates just to learn how to start making a half adder. Okay, so now I will see you later. I have to end it now. Goodbye, and see you later.